In late March, Grant Tremblay was sitting at his computer at his home in Cambridge, Massachusetts, listening in on a Zoom meeting, when he saw a string of emails pop up in his inbox. The title of each email read Cycle 1 JWST Notification Letter. He knew immediately that this was the day he and his colleagues in the astronomy community had been eagerly awaiting. It was Blacker Friday. Blacker Friday, to be clear, didn't have anything to do with discounts or Fridays. It was a Tuesday. It was the day that Tremblay, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, and other astronomers around the world, would learn if they would receive a small amount of time to use the James Webb Space Telescope, or JWST, one of the most powerful space telescopes ever created. We wanted to answer fundamental questions that cannot be answered any other way. Blacker Friday is named after Brett Blacker, who co-runs the Science Policies Group at the Space Telescope Science Institute, or STSCI. Each year, the institute is responsible for selecting which astronomers will get time to use NASA's Hubble Space Telescope. And each year, after a lengthy decision-making process, Blacker would send out a flurry of emails to hopeful astronomers, all on the same day at the same time, informing them if their proposals to use the telescope had been accepted or rejected. Thus, Blacker Friday, also sometimes known as the Blacker Apocalypse, was born. This year the stakes were even higher on Blacker Friday because for the first time ever, astronomers were being informed if they would get time with JWST, a brand new space observatory that is significantly larger and more powerful than Hubble. Set to launch to deep space at the end of December, the nearly $10 billion NASA-built telescope promises the ability to peer into the recesses of the universe like never before. Ahead of JWST's launch, STSCI had the daunting task of figuring out which of the 1,173 proposals for the observatory's first year of life, known as Cycle 1, should get time with the telescope. How do you prioritize what the most advanced piece of space equipment in the world should do when it first turns on? Well, the science has to be nothing short of revolutionary. What is deemed most interesting is science that is considered transformational, that will change our view of the universe. Klaus Pontoppidan, an astronomer and JWST project scientist at STSCI, tells The Verge. We don't want the observatory to do things a little better than what has been done before. We wanted to answer fundamental questions that cannot be answered any other way. The power of JWST. NASA plans to launch JWST the day before Christmas. But for the astronomy community, the launch is the real holiday. JWST is one of the most anticipated space science missions of the 21st century, as it has the ability to reshape astronomy and astrophysics as we know it. That's because the telescope is the closest thing we have to a time machine. Sporting a 21-foot-wide gold-plated mirror, JWST will be able to see in the infrared with incredible sensitivity. It'll be able to see objects that are 10 to 100 times fainter than what the Hubble Space Telescope can see, and it'll be capable of seeing things in 10 times better detail. It will gather light from stars and galaxies located up to 13.6 billion light-years away, light that has taken 13.6 billion years to reach the telescope's mirrors. Since the universe is thought to be roughly 13.8 billion years old, the galaxies that JWST will be observing likely formed just 100 to 250 million years after the Big Bang. Our universe was in its infancy then, and JWST will be providing us with the baby. Nearly every area of astronomy that you can think of will be addressed. In addition to peering back in time, the telescope will help us understand the large-scale structure of the universe, and perhaps tell us if it will go on expanding forever. It will peer into the centers of galaxies, finding supermassive black holes and helping astronomers learn how these enigmatic objects have evolved over time. It will observe the births and deaths of stars. It will even look back at our own solar system to study the faintest objects at the edge of our cosmic neighborhood, and it will be able to look at the edges of worlds orbiting around distant stars. Nearly every area of astronomy that you can think of will be addressed. Christine Chen, an associate astronomer at STSCI, tells The Verge. The promise of JWST has always been just over the horizon. Since an iteration of the telescope was first conceived in 1989, the road to the launch pad has been paved with cost overruns and technical issues. Naively, NASA originally envisioned a launch between 2007 and 2011, for a total cost between $1 billion and $3.5 billion. But JWST continued to miss one target launch date after next, while its total cost ballooned to $9.7 billion. As everyone waited for JWST to materialize, the world of astronomy blossomed. An entirely new field has emerged since the 1990s, one that revolves around the study of planets outside our solar system, or exoplanets. Since the first detection of an exoplanet was confirmed in 1992, we've discovered thousands of The Sephiroth worlds orbiting alien stars. In 2017, astronomers shocked the world when they announced the discovery of an entire alien solar system, consisting of 7 planets roughly the size of Earth all orbiting around a dwarf star. And 3 of the 7 planets, known as the TRAPPIST-1 system, sit in the star's habitable zone, where temperatures are thought to be just right so that water can pool on a planet's surface. After discovering such a bounty of exoplanets, astronomers are now eager to find what is referred to as Earth 2.0, a planet that's the size of our world, orbiting a star like our Sun at the right distance for liquid water to form. But exoplanets are incredibly faint, and traditional methods for detecting them, like watching stars dim ever so slightly as planets pass in front of them, can't tell us what might be lurking on their surfaces. JWST, however, is powerful enough that it may be able to detect light passing directly through the atmospheres of some alien worlds and use that light to say what kinds of chemicals are present in the atmosphere. Perhaps it could even detect signs of life. All of our transformational leaps in observational astronomy are enabled by making ever larger pieces of glass. It's a capability no one really envisioned when JWST was first being designed, but now it's considered one of the more exciting areas of science that the telescope will touch upon. It also means there are even more people who are very eager to get just a few hours with the most advanced space telescope over. All of our transformational leaps in observational astronomy are enabled by making ever larger pieces of glass, right, says Tremblay. And when you make a damn piece of glass that's large enough, and especially when you launch it into space, the discovery space for that observatory grows with time. It doesn't. Choosing the science. While JWST is ultimately a NASA mission, it's the Space Telescope Science Institute's job to determine what JWST actually does in space. You can think of us as sort of the software part of the observatory, Pontoppidan says, whereas NASA is the hardware part. However, STSCI had to wait a long time before figuring out the schedule for JWST's first year, and there were a few false starts along the way. When it seemed like the telescope would be ready to launch in 2019, the Institute called on astronomers to submit their proposals by March 2018. Then just a week before the deadline, NASA announced that the telescope wouldn't launch until 2020 at the earliest. STSCI abruptly postponed the deadline until a more concrete launch date was determined. Another postponement came again in March 2020, due to the onset of the COVID-19 pandemic. Finally, after what seemed like an eternity, astronomers turned in their proposals by November 24, 2020, 2 days before Thanksgiving. Then it was time for STSCI to sift through the more than 1,000 ideas that had been. STSCI knew that it couldn't handle this process alone. The Institute created a time allocation committee including astronomers and astrophysicists from around the world. They were separated into 18 panels, each one consisting of about 10 people, tasked with looking over proposals for different areas of space science and ranking them based on 3 important criteria: how much the proposal will impact knowledge within a subfield, how much it will advance astronomy in general, and whether the proposed idea requires the unique capabilities of JWST to be successful. Given just how many people want to use JWST, the Institute didn't want to allot time to an observation that could be done with any of the other telescopes currently online. We regret to inform you. With all of these benchmarks in mind, the committee got to work evaluating all of the proposals. To try to eliminate as much bias as possible from the selection process, the process was dual anonymous. That means that the people writing the proposals had no idea who would be evaluating them, and the people on the committee had no idea whose proposals they were analyzing. As a result, 30% of the winning proposals are helmed by women, and scientists studying for their PhDs also saw more success in getting their ideas approved. Now, since nobody knows who wrote the proposal, students can be just as successful as the mentors, Chen says. After painstaking debate, the committee selected the proposals it found to be the most transformative. It then gave each proposal a certain number of hours of observation time. Ultimately, STSCI selected a total of 266 proposals, submitted by scientists from 41 countries around the globe. Tremblay, the Harvard astrophysicist, had submitted 9 proposals for JWST's first year. On Blacker Friday, 9 new emails sat in his inbox. The emails don't come from Blacker anymore, but from the Science Mission Office at STSCI. He quickly clicked through them and read one after the next. Dear Dr. Tremblay, we regret to inform you. He read the phrase 9 times in total. It was a disappointment, but definitely not a shock. I wasn't broken up by not getting time this year, Tremblay tells The Verge. I knew it would be immensely competitive for Cycle 1, as it should be. And it's okay. We'll resubmit again. Nearly 2,000 miles away, Caitlin Casey, an astronomer at the University of Texas, was having a very different kind of Blacker Friday. She was at home in Austin, holding her sleeping 2-month-old baby in her lap while scrolling her phone. That's when she saw the email pop up in her inbox. Dear Dr. Casey, we are pleased to inform you. The ambitious project she and her team had proposed, called Cosmos Webb, had just been approved. And the Institute was giving Casey a whopping 208 hours. With JWST to fulfill her project the most of anyone who had submitted proposals. The project will stare at a particularly large patch of sky the size of 3 full moons, an area that spans up to 63 million light-years across. Doing so will create a portrait of the young universe similar to the Hubble's iconic Hubble Deep Field, which showcased some of the earliest galaxies we could observe at the time. With JWST's enhanced capability, the team will be imaging galaxies that are even older at even greater levels of detail. If the Hubble Deep Field were printed on an 8.5 by 11 sheet of paper, Cosmos Webb would be like a 16-foot by 16-foot mural on the side of a building, says Casey. All I had to say was we got it. Staying silent so as not to wake her sleeping child, Casey jubilantly logged into Slack and messaged her colleague and co-principal investigator on the project, Jahan Kardal-Tope, an astrophysicist at the Rochester Institute of Technology. All I had to say was we got it, Casey tells The Verge. She was dumbfounded too. And I think for the rest of that day, both her and I, we could not even focus. It was a flurry of excitement and just overwhelmed with that news. Aside from Cosmos Webb, the 7-planet TRAPPIST-1 system will be getting a lot of attention during JWST's first year, with up to 7 different programs dedicated to studying this strange cluster of worlds. JWST will be looking in the atmospheres of these planets, as well as dozens more we've found throughout the universe, hoping to determine if these places might be suitable for life as we know it. And there are hundreds more targets that JWST will observe, including galaxies, quasars, black holes, and more. While the committee tried to be as logical as possible with their final decisions, everyone agrees that serendipity does come into play. Probably there were a lot of amazing programs similar to ours that were also up for consideration, says Casey. There's always a little element of luck in the final selection process. Maybe someone on the panel just liked the specific way we presented some information. The first year, roughly 10,000 hours of observing time is allotted to different groups for JWST's first year of life. About 6,000 hours were given to the scientists who submitted proposals around the world, while nearly 4,000 hours were already set aside for scientists who helped design and build JWST and its instruments. The STSCI also has about 460 hours of discretionary time which have been allotted for what is known as early release observations. Data from these hours, scheduled to be done in the first 5 months of science, will become public immediately, so that anyone, even those who did not get time with the telescopes, can analyze Earth observations and write their own studies. Anyone who does the math will realize that 10,000 hours is actually more than the number of hours in a calendar year. STSCI purposefully overprescribed juices time to account for any snaffus. STSCI will be scheduling JWST's observations in 2-week increments, during which time the observatory will point at its intended targets autonomously. However, it's possible that JWST will fail to execute some commands properly from time to time. If that happens, JWST will simply go on to the next observation. And the Institute wants to make sure the telescope has fallback plans when such errors occur. We don't want to get to the end of the year and then run out of observations, Pontoppidan says. STSCI is also planning to carve out time for targets we don't know about yet. These are events like the explosive destruction of a star, known as a supernova, or when 2 particularly dense stars come together in a cataclysmic merger, known as a kilonova. If astronomers spot a particularly juicy supernova occurring in the sky, JWST's operators are prepared to reorient the schedule so that they can quickly observe the aftermath of the eruptive event. The prioritization of JWST's observations will be determined by the time of the year and where things are positioned in the sky. But as for the very first observation the telescope will do, NASA knows what it is but won't tell. It's supposed to be a surprise. While flexibility is going to be key for JWST Cycle 1, STSCI guarantees that all the proposals that have been approved will occur. Because each target in the sky is in JUICE's view twice a year, if for some reason a target is missed, there is a second opportunity to observe it 6 months later. If a target isn't observed in the first year, it might simply bleed over into next year. Basically, everything that gets through the committee, recommended and approved, will execute on the telescope, Chen says, as long as the telescope, works. If everything goes well with the telescope's launch, NASA plans to conduct at least 5.5 years of science with it, and hopefully up to 10 years. Ultimately, the observatory's lifetime is dictated by its limited fuel reserves, which are needed to help reorient JWST in space. Whenever that fuel runs out, JWST's mission will end. The community has immense demand for the telescope, and I think it's a great thing. that finality is still quite a ways off. First, JWST must launch and actually survive its trip through space. Once it reaches its final home 1 million miles from Earth, JWST will undergo 6 months of commissioning, when scientists meticulously test out the instruments on board, before the real science. And then, after a period of transformational science has passed, it'll be time to submit another round of proposals. Though Tremblay will be involved with one JWST proposal for Cycle 1 as a collaborator rather than the principal investigator, he does plan to submit his ideas again for Cycle 2. And he'll understand if it doesn't get accepted. As an astronomer, we get professionally used to rejections. I could wallpaper my hallway with rejections that I've received, Tremblay says. It's just a reflection of the fact that the community has immense demand for the telescope. And I think it's a great thing. Update December 20th, 1:50 p.m. Eastern Time. This article was updated to clarify the principal investigators on Cosmos Webb.